Nearly 20 years ago, I had a life-altering experience. A number of seemingly random events led to that moment. The first event, I attended my first Signal Integrity Conference in the spring of 2005 because of my concern about my level of expertise and that of my customers. There, I was fortunate enough to meet Rick Hartley, who immediately shook up my comfortable circuit theory-based world. The second event, Freescale planning its first worldwide customer event called Freescale Technology Forum for the summer of 2005. And my manager was on the content committee. He asked me to take his place during one of the calls. I was still very concerned about the changes in our technology and the issues I was seeing with signal integrity. So during a lull in the discussion, I declared that we had a responsibility to help our customers become more aware of this issue, and we should provide some training. The response was to task me with creating a panel of experts to address this issue. The third event, I really put my foot in my mouth here. I did not know any experts, but I could not let this opportunity pass by. To make it look like I knew what I was doing, I had been buying books on signal integrity and EMC, and my only recourse was to start calling authors and asking them if they would be interested in participating. One of the books on my shelf was Ralph Morrison's Grounding and Shielding Techniques, which I'd been told was a foundation text for any library. I found a phone number for Ralph, called it, and left a message. Ralph called me back and asked, "Who are you and why are you calling me?" I meekly answered, "My name is Dan Beeker from Freescale, and I would like to invite you to be part of a panel discussion on signal integrity and EMC." After some discussion, I was relieved to have him agree to be part of this event. The game-changing event. Ralph went first, since he was the one with the physics background. His listening to the other speakers led to his famous lament, jumping up and down, saying, they've got it wrong, that's not how things work." That was the event that shook my personal and professional world. From that moment, Ralph became an integral part of my life, sharing his knowledge and insight into the world of electromagnetic physics with me. His dedicated and caring approach to bringing me away from the dark side of circuit theory into the realm of real science led to a friendship that enriched my life. The bonus was meeting Elizabeth and being introduced into the world of music they shared, finding that I now had two very dear friends who became like family to me. From this first meeting, I took every opportunity I could to spend time with Ralph. I was able to contract him to teach his words of wisdom to my customers in Detroit, and he became a perennial contributor at the Freescale Technology Forums. These events allowed me to spend time with Ralph, slowly absorbing his wisdom. Ralph was patient, spending many hours with me discussing his perspectives on the science. I attended every one of his lectures, and whenever I traveled to the Bay Area, I made sure to plan a visit with Ralph and Elizabeth. An extra bonus was getting to share their music as they played with their friends in their home. One of the highlights of my life was a moment when Ralph declared, after listening to one of my presentations, "Dan, I think you finally got it." I was thrilled. Ralph often said I was the only person who listened to him. I find that to be a real mystery, as the insight and knowledge I gained from Ralph's patient mentoring completely changed my career. Adopting Ralph's perspective on electronics enabled me to become one of the most successful designers at my company. And more importantly, he provided me with a new set of rules to pass on to my customers. These rules are based on the simple statement Ralph had always used to end his seminars. Buildings have walls and halls. People travel in the halls, not the walls. Circuits have traces and spaces. Energy and signals travel in the spaces, not the traces. This was the missing link between electromagnetic field physics and circuit theory, missed by academia and industry alike. Once I could truly trust the simple fact, all the mystery disappeared and the true brilliance of Ralph Morrison became evident. I am honored and humbled by his appointment as his apprentice, and mourn the loss of my friend and the loss to the world of so much more we failed to glean from his profound knowledge. I will miss our talks, our tie outings, his lectures when I used the wrong word, and his support.
Back when I was a youngster, I saw that friends had crystal sets, and and I got my mother to put up the few dollars to buy a crystal set. I was enamored with radios and with things that made that radio work. I remember the very first radio the family got. It impressed me that information and music and whatever came through the airways in some way, and I wanted to understand that kind of mechanism.
And now I would like to introduce Elizabeth Morrison, my friend and Ralph's strongest supporter.
Thank you, Dan. I'm here to say a few words about Ralph's life so you'll know the background of that man jumping up and down and talking to Dan Beeker at that momentous occasion. But first, I'd like to say how happy it made Ralph to have Dan and also Ken and Rick recognize and use his ideas in the real world. It was his mission in life to bring the principles of physics to the electrical engineer. He had not given up on his mission before he met Dan, but I do think he was beginning to wonder if it would happen in his lifetime. Ralph was born in the Highland Park section of Los Angeles. His parents were immigrants from Ukraine. They were far from well off, but thanks to good public schools, he received an excellent education. He graduated from Eagle Rock High School, which is an international baccalaureate school, in 1943. And the Second World War was in progress, so he was drafted immediately after graduating. This made actually his whole class of 43 extraordinarily close throughout their lives. In 2018, we attended his 75th high school reunion of Eagle Rock High School. After his service and a year spent traveling around Europe as a violinist with the GI Symphony, he was able to enter Caltech on the GI Bill. His degree was in physics, as Dan said, and his studies there laid the foundation for his thinking throughout his career. He was a working engineer. He built and sold lots of instrumentation, as you can see him doing in this photograph, but he was always thinking about physics and questioning whether the assumptions of circuit theory in particular made sense. While working, lecturing, teaching, and consulting, he somehow found time to do a lot of writing. By the time he sold his last company, which was called Instrum, in the early 90s, he'd already written 4 books and brought out 3 editions of his groundbreaking book, Grounding and Shielding in Instrumentation. After retiring, he continued to lecture and consult. He wrote 4 more books and brought out 3 more editions of Grounding and Shielding. That's a new edition each decade from the 1960s into the 21st century. His default setting for most of our marriage was to get up each morning, work a Sudoku puzzle, go to his computer, and write another book. His final work, which was called Fast Circuit Boards, was published in 2018 when he was 93. Ralph's other passion was music. He began violin at age 4. His mother had taken up the instrument while expecting his younger sister, and Ralph said he wanted to play too. So his father found him a toy violin. He threw it on the floor. He did not want a toy. Somehow a quarter-size violin was found for him, and he never stopped playing his whole life, even during the war. The photo on the left shows him in the GI Symphony. After returning home, he joined an ensemble led by Julian Brodetsky. This is the photo on the bottom, which is where he first met the late Beethoven quartets, which were his joy throughout his life. The photo in the text shows him preparing for a violin recital he gave to celebrate his 90th birthday. Ralph and I met playing a Beethoven string quartet. We played so much music together over the 30 years of our marriage. Ralph loved sharing music with friends, and it was a source of great pleasure to both of us. When Dan would visit us, he always asked to hear us play, and we were always glad to do so. Ralph was a wonderful musician, a wonderful engineer, and a wonderful husband.
One of the things we were able to do, because in my opinion, Ralph had been one of the most underappreciated engineers and scientists in our industry, was I brought to the attention of NXP management that we had a wonderful opportunity during one of our conferences in Silicon Valley to honor Ralph. When I presented this idea to the managers, they were absolutely 100% behind this. And one of our marketing managers then proceeded to deliver a Lifetime Achievement Award to Ralph. And this is a picture of him receiving that award.
But Dan's needs
Ralph wrote after we met. He decided that he was going to take the current technology and apply his perspective. And this was the result: fast circuit boards. Always the central point was his mantra: buildings have walls and halls. People travel in the halls, not the walls. Circuits have traces and spaces. Energy and signals travel in the spaces, not the traces. This simple fact was so heretical compared to the beliefs and teachings of most universities regarding energy in electronic circuits that it was very difficult for me to make the transition from the traditional electrons flowing in wires to energy moving in a space. It took almost 10 years of Ralph's patient tutoring for me to be able to become very confident and secure in the idea that the science was right and following the simple rules that he provided would result in success. So they boil down to a very simple picture here. And when I look at this, to me, it's still very profound. And the idea is that we use conductors to direct the fields. So in a good system design, there are three elements that are used to contain field. There's a conductor, a space, and a conductor. And on the left-hand side, you can see those three elements. It's the rule of triplets. In electronic circuits, you only have three components. You have a conductor, a dielectric, and a switch. So in the middle is the switch. Until the switch is closed, the field energy on the left will be very happy to stay put on the left-hand side. As the switch is closed, the field starts to see a need for it to move into the new space. So a switch, instead of closing a circuit, actually connects a space where the energy is not present. So the field energy really wants to become equal throughout the entire space. So as the switch closes, the field energy will move sequentially into the new space until equilibrium is established. As the energy continues to move through the dielectric, we can control where this energy goes by managing carefully the three elements of the circuit board. One is the continuous conductor, which sometimes we call ground. Adjacent to that continuous conductor must be the continuous dielectric, which is the space where the energy will move. Adjacent to that dielectric is what I call the switched conductor. This is the only thing we get to control in our designs. By using the switches, we can connect or disconnect the spaces where we want the energy to move. When the switch is opened, the energy flow stops and there will be field energy on either side. And depending on what is at the end of this transmission line, the field will either become static because it's not moving, or it will continue to be moving through the board structure. You can only do three things with field energy. You can store it between two conductors. You can move it as you provide a new space to allow the field energy to move forward, or you can convert it into kinetic energy. And that's basically the entire electronics world. From what Ralph taught me, this is not rocket science. This is some very simple geometry-based rules. And when you think about designing the dielectrics as opposed to designing conductors, the results are nothing short of miraculous. Here's the bottom line. We were taught that when you close a switch, the energy starts moving in a loop through the conductors. If that were true, there would be no issues with signal integrity, and we would have no problems with radiated emissions. But at the same time, there would be no such thing as radio. So every day we prove to ourselves that circuit theory is not a correct perspective, because radio is something that we live with. The energy used in radio is electromagnetic field, and it travels through space. Just because we start to move the same energy on a circuit board, it does not magically change into electrons moving in wires. It is still electromagnetic field energy moving through a space, which hopefully we designed on purpose. When you turn on a switch, you've added a new space and the energy flows into this new space. So this is the bottom line here. The rules of triplets. You can use one hand 3 times. You only get 3 components to control the energy: a conductor, a dielectric, and a conductor. Field will sit there very happily. There's only 3 components. You get a conductor, a space, and a switch. And again, you can only do 3 things with electromagnetic field energy. You can store it, you can move it, or you can convert it to kinetic energy. You use the energy to heat up wires and make lights work. You use the energy to move motors or to vibrate speakers. Pretty much that's the only thing you can do with it. And if you manage the dielectrics properly, the energy goes where you want it to. If you size the dielectrics properly, you move enough energy to do the work that you need, and your circuit boards and your systems will behave properly. As I said, it's not rocket science. It's very simple applied physics. So what we have to remember is that everything is a transmission line. And it needs to be a transmission line that we created on purpose. It's not the basic circuit point of view, which doesn't care about the space, but just looks at the connection of the conductors. What you have to do is to make sure that you have a specifically and purposefully designed dielectric space, bounded on one side by a continuous conductor and bounded on the other side by the switched conductor that we use to allow the field to move, or we stop the field from moving.
So thank you very much, Dan, for this introduction and explanation. And now we will be hearing from Ken.
Thank you, Lucy. I originally learned of Ralph's teaching through Dan Beeker, who teaches with me during the annual EMC Week training seminars in Boulder City, Nevada. I was also fortunate to be able to participate in what was Ralph's last public seminar on the subject. Later, I attended Rick's two-day seminar on PC board design and forever became an advocate of the field's point of view for PC board design. I'll be forever indebted to Ralph, Dan, and Rick as we help move product designers towards physics-based board design. With that, I'll continue with my slides here. As Dan mentioned earlier, all board traces and planes are transmission lines. Most of us were probably taught in our DC circuits class that current travels through wires from the source to load and back. And this is true for theoretically pure DC. It may also have been implied that the current travels at or near light speed, which is false. However, once we start to reach beyond 10 kilohertz AC or so in frequency, we need to start thinking in terms of signal propagation as electromagnetic waves. In order to propagate the field energy within the signal's electromagnetic wave, it must be trapped between two pieces of metal. In the usual case, for circuit boards, between the copper microstrip and return plane. So we have the circuit's point of view, where digital circuits and power require a return path back to the source, and we have the field's point of view, where the signal and power transient fields travel in the dielectric space at near light speed, while the conduction and displacement currents simultaneously flow back to the source at only about 1 centimeter per second. Think about wave propagation like throwing a rock into a pond. As the wave radiates out from the point of impact, the waves propagate along the surface. The water molecules don't actually move with the wavefront. They just move up and down in place. And the same basic concept occurs as signals propagate through circuit boards. The important point is that the digital signal energy is in the fields, not the copper. The next slide shows the physics involved. It's important to understand the physics of electromagnetic wave propagation in circuit boards. To understand how digital signals propagate in circuit boards, we first need to understand how current appears to flow through a dielectric layer. Consider the figure on the left. When we close a switch, current will start to flow, building up a positive charge on the top plate of the capacitor. This positive charge repels any positive charges on the bottom plate, thus resulting in negative charges remaining. An AC or digital signal will cause the charges to alternate, thus appearing to conduct current. Maxwell called this effect displacement current. Now, referring to the figure on the right, if we apply a digital signal or wavefront with leading edge going from high to low to the microstrip, an electromagnetic wave will be launched and will begin to propagate through the dielectric space between the microstrip and return plane at about half light speed for the typical FR4 dielectric. As the wave propagates down the microstrip, conduction and displacement currents will be induced via electron flow in the copper molecules. Because copper electrons are pretty tightly bound, there will be electron flow, but at very low speed of about 1 centimeter per second. This is the current we measure with an ammeter. The location of the displacement current will move at near light speed, following along with the wavefront. It is important to note that breaking this return current path will cause field leakage of the electromagnetic wave, generation of common mode currents, and an increase in EMI. I'll show the dramatic increase in EMI as a result of a break in the return plane later in this presentation. As Dan described, the rules of board design are relatively simple. Every signal trace needs an adjacent return plane or trace in order to contain the field. And every power trace or plane needs an adjacent return trace or plane to contain the transient field. Most importantly, this also includes return paths up and down through layers when signals transition from the top to bottom layers. And this would require the addition of ground stitching vias for return-to-return layers and stitching capacitors for return layers. These rules will dictate stack-up design. And this is where many PC board designs cause EMC compliance test failures. Very few of my clients get the stack-up right. Here's the typical 4-layer stack-up IC. From top to bottom, we have signal, ground return, power, and signal. This is a very risky EMI design, as Rick will mention shortly. The first issue is that for the usual 62 mil thick boards, the power and return planes are spaced too far apart for good high-frequency decoupling. Second, the bottom signal layer is referenced to power rather than ground return. Most digital signals want their return currents referenced to digital ground return rather than power. When referenced to power return, currents must find their way somehow back to the source, and this convoluted path usually ends up causing radiated emissions and susceptibility problems. The only time I relent and allow signals referenced to power is when the power return planes are closely spaced at 2 to 3 mils max and with adequate decoupling capacitors, or if the signals are low frequency. And with 62 mil thick boards, this is not the case. If your budget dictates a 4-layer design, the EMI issues may be fixed by substituting the power plane for a second ground return plane. Thus, we have 2 signal layers with routed power or power polygons and 2 ground return planes. Because we lack closely coupled power and return planes, the most important consideration is to include sufficient decoupling capacitors at the power pins of ICs. There are 2 considerations: placing the 2 return planes on the inside layers, as in the top figure, or placing them on the outside layers, as in the bottom figure. I guess you could also make the stack up signal return as well. The advantage of having the 2 return planes on the inside layers is that the signal traces are easier to get to for troubleshooting purposes. On the other hand, if the planes are on the outside, they may be stitched together around the edges to simulate a Faraday shield. Most 6-layer board stack-ups I see when performing EMC design reviews are that shown on the left, another poor stack-up design. The top 3 layers, signal, return, signal, are fine as is. The issue occurs in the bottom 3 layers, where again we see the signal layers referenced to power. Also, with the power and return planes separated by up to 40 mils in a 62 mil board, you would expect very poor high-frequency decoupling. Also bad news for EMC. A new problem surfaces though, and that is the fact that there are 2 signal layers between power and ground return. So what do you think happens when we have power transients occurring between the power and ground return planes in layers 2 and 5? That's right, power transients coupling to signal traces in layers 3 and 4. A better design for signal integrity, power integrity, and EMI is the board design on the right. Note that every signal and power layer has an adjacent return plane, so all propagating fields are nicely trapped as the electromagnetic waves propagate from source to load.
Thank you very much, Ken. Now we will be hearing from Rick.
Thank you very much, everybody. Before I start on the picture on the screen, I would really love to just take a minute to talk about Ralph. I met Ralph shortly after Dan did. Dan came to one of my talks at PCB West, I believe it was 2006, and he brought Ralph with him. And just as Ralph jumped up and down at the Freescale Technology Forum, he jumped up and down in my class too, saying, "You've got it wrong." And I wasn't quite sure what he meant. And so we ended up having a meal together that day. And over the meal, Ralph said to me, "Rick," he said, "honestly, I really like much of what you presented today. You have a lot of really good material and a lot of really good ideas. However," and there's that word however or but, which means that everything that came before it didn't matter. And he said very carefully and very, very clearly, "You're talking about energy being in voltage and current, and it simply is not in the voltage and current. The energy is in the fields." I'm going to tell you, it took me a long time, just as it did Dan, to shake what I had learned in college and what I had learned from every engineer I worked with over my career. The idea that the energy was in the fields was really tough for me to deal with. It took me literally, and I'm not exaggerating, years to get used to the idea. Once I did, I really began to understand exactly what was going on in the circuit. Suddenly, once I understood fields, suddenly every problem I had seen in my life, I could explain. Up to that point, I had a lot of trouble explaining to people why this problem or that problem occurred. Good example, circuit A and circuit B on the same circuit board have absolutely no copper connections between them. No power, no ground, nothing connecting between them, and yet one interferes with the other. How is that possible? Well, in circuit theory, it would be easy to explain if they were connected. If they aren't connected, circuit theory can't explain that interference, but field theory can. And once I finally understood field theory, suddenly everything in my life made sense, and all the problems I'd seen made sense. And frankly, I've been designing using field theory for many years now and haven't had any problems as a result of it. And I don't expect to at any point in the future. And I just want to take a minute to say how very much Ralph meant to my life. He truly, literally changed who I am, what I am, the way I think, and the way I teach. And people who attend my classes now tell me repeatedly that they gain a lot of really good information because I'm basically teaching them Ralph's thinking and Ralph's theories. And I will forever be humble to that wonderful man. So looking at this 4-layer board, Ken talked a bit about the problems with a conventional 4-layer board with power and ground on layers, pardon me, 2 and 3. And he's absolutely right. There are many problems with that board, one of which is the high impedance power bus, which I will address that in just a moment. In 1995, I was working for Goodrich Aerospace, and we had a very low-cost product that we had to design and build and ship. And it was decided that the main board in it, there was one board and a couple of small boards with power and so on. And the main board was going to be a 4-layer board. So I designed it as a conventional 4-layer board with power and ground on 2 and 3. And we were failing EMI by 6 or 8 dB. I mean, it was horrendous. And we weren't just failing at a frequency, we were failing at a half dozen frequencies or more. It was really bad. The group of engineers in the company, myself included, got together and talked about what we can do about it. And we kicked around a lot of ideas, and someone brought up the concept of, what if we could move the signals from the outer layers to the inner layers? Instead of making them microstrip, make them strip line. And I thought about that and realized strip line are inherently quieter because, and I didn't even realize the concept of fields then, but I knew the energy was better contained with strip line than it is with microstrip. And so I started working on that thought. And I brought the board up on the screen and I disconnected the ends of all the traces where they connected to the components. And I moved the signals from 1 to layer 2. And I moved the signals from 4 to layer 3. And amazingly, when I turned the top two layers off where the components were, suddenly, as I looked at these two signal layers, I realized, my God, there is a ton of open space on these two layers because they don't have all those pesky components in the way taking up space. When these signals were routed with the components, between the components and the signals, they consumed every square millimeter of space on both the top and bottom of the board. But when I moved them to the center two layers, suddenly it's amazing how much open space there was. So that's when I got the idea, wait a minute, let's pour ground with copper pour on the top around the components and on the bottom. And the beauty of it was the signals had already been routed in a place away from the components. So all of the signals now beautifully referenced that ground pour that I had just put on the board. And then when I was done, I thought, wow, this is great. What am I going to do about power? And then it hit me. I've got all the open space on layers 2 and 3. Let's do copper pour on those layers and make that the power. Well, when I first did it, not every power connection was made because some of the signals got in the way of power pour. I had to move some signals around and do this and do that. But eventually, I came up with a design that had signals and power on layer 2 and layer 3 and the ground on layer 4. And it worked brilliantly. And here's the best part. When we went to EMI testing, we got a 14 or 15 dB improvement in the EMI signature. And we passed EMI testing easily with this board. I'm not going to sit here for a moment and tell you that this is an easy design. People who design with signals on top and bottom and power and ground on 2 and 3, they're making their life easy. That's easy to do. Do you want easy or do you want something that will actually work? This is another version of that same board, and Ken talked about this as well. The nice thing about this, as he pointed out, is that you have signals on the outer layers for easy access. The downside to this is that it only works in low density designs. Think about this. You have components, you have signals routed, and you have power all on the outer layer. Now, there's two ways, as Ken pointed out also, you can do power. You can route power in the case of lower frequency components such as microcontrollers and devices that have edge rates that are 2 to 3 nanoseconds. You can route power because you can properly place decoupling to allow you to route power and get excellent results. With higher speed parts, microprocessors and other things, you're really going to have a tough time routing power. You're probably going to have to pour it. So whether you're routing or pouring power, this design on the right works brilliantly, but it only works for low density designs. The one on the left works in many scenarios. Once I came up with this concept of the design A on the left in 1995, once that was realized, I've probably designed 50 circuit boards like that since, and every single one of them has worked absolutely flawlessly. It's just a brilliant design. Ken also mentioned the power bus, the plane impedance, when you have a conventional 4-layer board with power and ground on layers 2 and 3. If you do the board stack up as either of the ones on the previous slide, the power bus impedance improves from the gray line next to the red line. And the beauty of it is that when you put power on 1 and 2 and 3 and 4, in other words, power ground, in any combination, you will improve the power bus impedance by anywhere from 5 to 6 times improvement. This is a logarithmic scale. And this may not look like a massive improvement, but it is a massive lowering of the impedance. So 4-layer boards of that type, again, harder to design, but much superior in their capability. This is a 6-layer board that Ken also mentioned. That's the poor design. And as he discussed, one of the problems is having signals between the power ground planes. And a second problem is having the power and ground planes separated by, in this case, about 50 mils, 45 to 50 mils. That's an enormous spacing. You can take this same board stack and by putting copper pores on the layer 1, layer 3, layer 4, and layer 6 signal layers and attaching those to the power that you need to distribute, you can attach the top two pores to ground and the bottom two to power. You end up now, instead of delivering power from, and one of the questions I ask people in my sessions that I teach, when I bring up a board like this, where does power come from? And most of the people in the room will say, the power plane. The answer to that is incorrect. The energy does not come from the power plane. It comes from the dielectric space between the power plane and the ground plane. The design on the left, the energy gets delivered in the dielectric between 2 and 5, as Ken pointed out. The problem with that is power bus switching transients, as he also mentioned, can couple into signals. With the stack up on the right, power no longer comes from 2 and 5. Power, because of the copper pores, now comes from a dielectric space between 1 and 2, between 2 and 3, between 3 and 4, between 4 and 5, and between 5 and 6. So you get 5, and even though each of those areas is smaller areas of delivery, you end up with 5 much more closely spaced dielectrics delivering power, which drastically lowers power bus impedance. And here's the best part. The signals in the middle of the board, if they're distributed properly, where they reference a plane above and a plane and a power pore section below, those signals are no longer suspect to being interfered with the power delivery from those dielectrics, because now the power is being delivered next to the signal fields, not over top of. And this makes a major difference. This is still not what I consider an ideal 6-layer stack up, but it is a massive improvement over the previous stack up. This is the power bus impedance of planes on layers 2 and 5. That would be the board stack we just talked about on the left. This is what happens when you go to the power pores on each of the layers, and now are delivering power from the dielectrics from 1 to 2, 2 to 3, 3 to 4, and so on. The overall response raises the capacitance of the planes and drastically, and most important part, drastically lowers the inductance of the power planes. And the result is this is an order of magnitude improvement. This is a times 10 lowering of the power bus impedance. Is this fantastic? Is this going to work at gigabit speeds? Heavens no. This is not going to work at gigabit speeds, but this is a massive improvement for simpler board designs of the type that many people often find themselves dealing with. This is an 8-layer board stack up that I'm particularly fond of. Most people will put signals, ground, signal, power ground in the middle, signals, ground, signal. To that, I usually add the copper pores on the signal layers, and I alternate them as power and ground. So once again, you're not getting power from just the center of the board. You're getting power from all 7 dielectrics in this board, and it's being delivered through a much lower impedance path, which is a drastic improvement in power delivery, and it keeps the signals away from power and so on and so on. This is another 8-layer design that is a distinct improvement even over the one on the left. The reason we've gotten rid of the power plane entirely, and now everything in the board references ground. The only downside to this is if you must have a power plane to distribute power, if you can't get it done with power pores, then this is going to be a challenge to make work. But as long as you can do it with pores, this is a magnificent stack up. And this is my favorite 8-layer stack up. Signal, ground, signal, ground, signal, ground, signal, ground. Every other layer is ground, and everything references ground. You could invert the bottom 2 if you really need for the outer 2 layers to be signals, or you could use the stack up in the middle. I prefer this one on the right. You can take 2 layers away from this and make an excellent 6-layer board as well. You can add 2 more layers just like this and make an excellent 10-layer board. This is an 8-layer stack up, and I'm not going to say who it was, but there's a major IC company. The last project I worked on prior to retiring, we had a 1300 pin microprocessor from a major IC company. And in their 100-page app note, they referenced this board stack up and said, we know some people must have low layer count because of cost. This is the smallest layer count we were able to route this 1300 pin processor on. I can understand that if they had enough on package and on die capacitance, that they might have, from a signal integrity point of view, been able to get this to work. But it's clear to me that they did no EMI testing. And the reason I say that, there is not a chance in the world that this board could pass EMI testing. Why do I say that? Look at power plane 1. Where does power from that plane come from? Again, don't say it comes from the copper. It comes from the dielectric between that power plane and the layers above and below it. Some of the fields from power plane 1 will couple to ground, but the majority of them, because of proximity, will couple to power plane 2, which means the majority of the return current from power plane 1 will be in power plane 2. And the same thing is true of power plane 2. Most of its fields will couple to power plane 1. Is this a good idea? I don't think I need to tell any of you it is not a good idea. First time I presented this, a gentleman said to me, it's an 8-layer board, Rick. You have a core in the middle. You can make that core thick and widely separate power 1 and power 2. Correct. But when you do that, now where does power plane 1 couple? To the ground plane on 2. What is in between power 1 and that ground plane on 2? Aha, a signal layer on 3. That means the signal energy is going to couple into the power bus, and the power bus transients are going to couple into the signal. This is an almost guaranteed EMI failure. Every time I do a public forum, public presentation, I mention this company by name, and I say, is there anyone in the audience from this organization? And usually 1 or 2 hands go up. And I say to them, go back to the company, find out who proposed this, prove that you guys did EMI testing and that you passed, and I'll quit talking about you. But until you prove me wrong, I intend to continue throwing your name out in a negative light. This is a 10-layer stack up from a client that I had a couple of years ago who had major problems with a board. When I get a call or an email from someone saying we've got this or that problem, the first question I ask them, what is your board stack up? I took one look at this board stack up and immediately knew what was wrong. The power planes in this board, problem number 1, reference each other. Notice on the center 2 layers, there are signals. Half of each one of those layers were power planes. And they reference the power planes above and below them. So all of the signals on layers 5 and 6 reference the power planes on 4 and 7. That is a terrible thing to do, as we've already talked about. And not only that, the power planes that were on those center layers reference the power planes above. If that's not bad enough, the routes that are on layers 3 and 8 reference power more than they reference ground. So the majority, because of spacing, the majority of their fields are going to be coupled to power planes. And if that's not bad enough, those signals are trapped between the signals on the power and ground on layers 2 and 4, and then again at the bottom of the board. When you look at this, it's obvious. This is everything wrong in the world. Whoever decided in the first place that this was a good board stack up was absolutely not thinking clearly. If that's not enough, as this bottom comment says, the top 2 dielectrics are 2.5 mil prepregs. It's tough to contain and hold prepregs to exactly 2.5 mils. Their intent was to get 50 ohm lines on every layer. And as you can see from the comment on the left of this diagram, the top and bottom layers were 45 ohms. The next signal layers were 38 ohms. And the only place they had 50 ohm lines were in the middle of the board. But of course, those particular lines referenced the power planes above and below. This is a horrendous stack up. You have to think about the fields. Where will the fields exist? As Dan pointed out, as Ken pointed out, signals and power should always reference ground. Think about designing stack-ups where that is possible. Thank you very much.
Well, thanks, Rick. Very educational. Aside from the stack-up problems described earlier by Rick and myself, one of the biggest design issues I find during reviews is clock or high-speed digital signals crossing gaps in the return plane. Now, we like to have a solid return plane. So at this point, I usually perform a live demo, but I'll try and do my best with diagrams and an actual measurement result. When we have a clock crossing a gap in the return plane, the gap forces the return conduction current out around the gap. This causes mutual inductive coupling on each side of the gap, which in turn produces a small voltage source that converts the differential mode or signal currents to common mode currents throughout the board. These stray currents tend to escape out I/O and power cables, causing radiated emissions and an increase in susceptibility to things like ESD and radiated immunity and other external energy sources. I've tried to depict the electromagnetic fields as curved red lines between the clock trace and return path. In the next slide, I'll show the test setup. Let's consider a two-layer board with two 50-ohm transmission lines. At one end, we have BNC connectors, and at the other, 50-ohm loads. The top transmission line has a gap cut into the return plane. When I connect a pulse generator with 10 megahertz harmonics to the BNC connector for the ungapped trace and probe along the transmission line with an H-field probe, we'll see a set of harmonic signals spaced every 10 megahertz from the source to the load. Probing the unconnected gapped trace will show very little coupling. So now let's connect the pulse generator to the gapped trace. We'll see an increase of 10 dB in harmonic energy at the gap, but more interestingly, we can see major coupling to the now disconnected ungapped trace. Finally, let's connect a clip lead to the return plane to simulate an I/O cable and measure the harmonic RF currents in the wire. When driving the gapped trace, we'll see an increase of 10 to 15 dB when compared to driving the ungapped trace. This could be the difference between passing and failing the radiated emission test. To see this demo in a recorded video, just click on the link or go to my website, www.emc-seminars.com, and find the videos tab. This plot shows the difference between driving the gapped versus the ungapped traces. The gap in the return plane is causing common mode currents to form, which then flow out along the attached wire. Placing a current probe around the clip lead shows the high frequency currents flowing through the wire, which cause the wire to become an antenna and radiate. In the spectral plot, we're looking from 30 to 1000 megahertz. The violet measurement is when I'm driving the gapped trace, and the aqua measurement is when driving the ungapped trace. And you can see a 10 to 15 dB difference throughout the spectrum. Note that common mode currents are the dominant cause of radiated emissions, and poor PC board design is usually the root cause. Now that's just the results from a single gap. You can imagine what happens if you have multiple gaps in your return plane. Here are several useful references that include additional information on how signals propagate in PC boards. Ralph Morrison's book, Fast Circuit Boards, is excellent. And there are several others by Dr. Eric Bogatin, the Johnson and Graham High-Speed Digital Design book, and also Schmidt, Electromagnetics Explained, has good explanations of the field point of view. As far as I know, there are only the three of us teaching PC board design from a field's point of view. We all provide public and in-house seminars which cover much more detail than we've been able to touch on today. And we'd invite you to use these references to find out more on this topic.
So the picture on the left is one of my fondest memories. We were finally able to convince Ralph that we should allow him to do a presentation and video this event. And he came to Detroit with Elizabeth, and Ken was one of the participants. And this was our celebration after we had done the videography of this 3-day class. And these sessions are actually available on Ralph's website, which we'll show later on. And then to the right is one of my very happy moments. This is Ralph after he received his Lifetime Achievement Award from NXP, and he's holding his award there. And both of us are very proud. At this point, I feel kind of like the proud papa, because the idea of getting Ralph's teaching into the world sort of fell on my shoulders, and I was extremely happy to get NXP to provide some very visible public recognition for his work. So this is like the fearsome foursome on the left, and I'm with my mentor one of my last times.
Dan, those were such happy occasions for us too. I was really glad that you, after much discussion, really years of discussion, you were able to organize the videotaping of Ralph's work, and that was just great. And also, I was very happy to be at the presentation of his Lifetime Achievement Award. Ralph was so glad for all these opportunities that were provided for him to spread his mission of bringing physics to the electrical engineer.
They were well-deserved moments.
I might add that while I was editor of Interference Technology, we invited Ralph to be the keynote speaker during a series of webinars, and that recorded presentation is on his website right now.
Good.
I want to say to thank you to Elizabeth for sharing Ralph with us.
Yes.
and helping him to continue his career long past anybody else's expectation. So I know that I was really single-handedly responsible for dragging him out of retirement, and it was absolutely worth it to me and to the entire industry. And it's a pleasure and an honor to have been part of your life, Elizabeth, and Ralph's life. And through this, I met Ken and Rick, and the collaboration we've been able to do together has been, like several of us have said, just life-changing.
Yep.
And following these rules on my systems that I design, I have 100% success in compliance. And when I work with my customers and they follow the rules as I try to present to them, they have 100% compliance.
Right.
And it doesn't get any better than that. We continue as a team to prove that physics is real and the rules are very powerful, and circuit-based designs continue to fail. And this is my challenge to the industry. The status quo has become failing EMC.
Right.
And that's not engineering. I have customers who may go 3, 4, 5 different spins on their circuit board before they get compliance. And each time they do the new design, they have absolutely no confidence that they're going to pass.
Right.
And to me, that's not engineering. And the sad part is they're continually willing to pay for these emergency respins of their circuit boards but they're not willing to pay for their engineers to get the training that would enable them to be successful. So this is the message out there. Stop spending money on failures and spend some time studying the science, and you will be rewarded with higher profit margins. Companies go out of business every week because they can't make their market window, or it's cost them far too much to develop these products. So all I can say is follow Ralph's rules, and it is all about the space.
Yep.
My parents never had an education to any extent, and so I was essentially on my own, and it was up to me to make the connection with the technology, with education, with what was going to happen to me in the future. So I was able to probe, you might say, the environment I had, and to use the interests I had to converse with teachers. And good teachers will take that piece of information and extend it and give you more opportunity. I found that was true in the electric shop, where they made this opportunity for me to run this Tesla coil, or to build a square wave generator, or to do things which were really above and beyond what I was capable of, but they were willing to at least expose me to that real world.